This is lesson 4.4, spanning sets and linear independence. The focus of this lesson is really on that latter part, looking at what makes a vector space linearly independent. But before we get into that, we first need to look at a couple of other ideas. Firstly, what does it mean to be a linear combination of vectors? And then lead that into this idea of a spanning set. Once we have those two topics covered, then we'll dive into that whole thing on linear independence. So let's start off with a definition on linear combinations of vectors. I'm not actually going to read this definition. Bottom line, all this is saying is that to be a linear combination just simply says to take one vector and write it as the sum of other vectors being multiplied by scalars. We've actually seen this concept before in other situations, and so I'm going to just dive right into an example just to make this crystal clear. Let's go ahead and take a set S, and we're gonna work primarily in the 3 space throughout this lesson. So we're going to do vectors of 3 elements here. So let's make our first vector 1, 3, 1. Let's make our second vector 0, 1, 2. And let's make our third vector 1, 0, negative 5. All right, so the idea then is if I have a vector, and I'll just make a fourth vector here, W, and we'll call this 5, 5, negative 15. So this vector W is a linear combination. It's a linear combination of, let's call this V1, V2, and V3. Oops, V3. It's a combination of V1, V2, V3. Because we can basically take these 3 vectors in S, multiply them by particular scalars, add them together, and get W. So in this case, obviously I've done this already to know what this is, but I can take V1 times 2. I can add to that V2 times a negative 1. So 0, 1, 2. And then I can add 3 times V3. And that will give me vector W 5, 5, negative 15. So just to show this, to kind of test this, if we just look at the first element, we'd have 2 plus 0 plus 3 is 5. Okay, and it would obviously work then for elements 2 and 3 if we were to check those as well. But that's the idea of a linear combination. So we'd say that W is a linear combination of those other 3 vectors because we can multiply those 3 vectors by scalars, add them together to get W. All right. So let's do an example then where we don't know what the scalars are, and we're going to find the scalars that would create that linear combination. So we are going to write vector W, which we're going to define as 1, 1, 1, again staying in that 3 space, as a linear combination. It's a linear combination of V1, V2, and V3 from above. So we're going to use the same vectors we just used from example 1 and use those to create this W defined as 1, 1, 1. So just like we have up here in example 1, we were able to multiply by 2, negative 1, and 3 to get 5, 5, negative 15. We're going to try to find the scalars now to get 1, 1, 1. So I don't know what those scalars are, so we're just going to call them C1, C2, C3. So we've got C1 times vector 1, C2 times vector 2, and C3 times vector 3, 1, 0, negative 5. And we want that then to result in this vector W, which is 1, 1, 1. So hopefully now, this far, and we've done a lot of things kind of similar to this. We're starting to see what we want to do here, and that is to write a system of linear equations. So again, if we look at the first elements, we have 1 times C1 plus 0 times C2, so there's no C2, and then plus C3, and that equals 1. For the second element, we'll have 3C1 plus C2, and no C3 equals 1. And then for our last equation, we'll have C1 plus 2C2 minus 5C3 equals 1. And now we're just going to solve the system to find the scalars that make this true. So I'm going to make an augmented matrix here. We're going to go 1, 0, 1, 1, 3, 1, 0, 1, and 1, 2, negative 5, 1. And again, if we apply Gauss-Jordan method here, what we end up with is the matrix 1, 0, 1, 0, 0, 1, negative 3, 0, and 0, 0, 0, 1. So in this case, because we have that row, that last row of 0, 0, 0, 1, that actually tells us that this system is inconsistent, that there actually is no solution to this. In other words, there's no scalars C1, C2, C3 that we can multiply those three vectors V1, V2, V3 by, adding them to get 1, 1, 1. Just completely impossible. All right? Obviously, if we had gotten a consistent system, a matrix that actually showed us solutions, then we'd have that linear combination. All right, we're going to come back to this in just a little bit and make some connections to this with this next idea of spanning sets. So now that we understand, hopefully, what a linear combination is, let's talk about this idea of spanning sets. So our definition says let S equal V1 be the set from V1 to Vk. And this is going to be a subset of vector space V. So the set S is a spanning set of V when every vector in V can be written as a linear combination of vectors in S. In such cases, it's said that S spans V. Okay, so again, all this is saying is and we're going to stay in R3 still. Let's suppose we consider V to be all of the vectors with 3 elements in the 3 space. If I can find a subset within that, whether it be 2 or 5 or 12 vectors, however many it needs to be, where I can write every single vector in V as a linear combination of the vectors in that subset, then that subset S spans V. It's a spanning set of V. That's what this is saying. So just to give you a couple of really simple, straightforward examples here, let's suppose that our subset S is defined by the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So these are all, again, obviously in R3. So we're going to say that this spans R3. Okay, so I'm already kind of jumping to the conclusion here that S is a spanning set of V. And I'll show you why. Okay, so we say that S spans R3, this is basically V. Okay, this is our vector space V, because any vector, and I'll just call it U, that has the components U1, U2, and U3, also in R3, can be written in this form. So I can say that U, so U just represents any vector in V, in R3. And I can write a vector by taking U1 times the vector 1, 0, 0, plus U2 times the vector 0, 1, 0, plus U3 times the vector 0, 1, 0, 0, 1, excuse me. And this is going to give me every single time U1, U2, U3. So in other words, we say then that subset S, that this thing right here, is a spanning set of V, or it spans V, because we're able to show that no matter what vector you pick in V, we can write that vector as a linear combination of those 3 vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. Let me give you one more example like this. So let's consider a different situation. Let's go away from the R space, and let's talk about polynomials. So I'm going to define this to be the subspace S, 1x and x squared. And in this case, we can say that this spans P2, in other words, all polynomials of degree 2 or less, and again, that's kind of our vector space V, because, again, every polynomial basically or I'll say it this way, that every polynomial function is basically written as P of x equals a plus bx plus cx squared in P2 can be written as P of x equals a times 1 plus b times x plus c times x squared, okay? Which is going to give us, obviously, a plus bx plus cx squared. Now, let me just kind of make clear what I did here. So basically, I created this subspace, 1x and x squared, and we know that a polynomial in the second degree is written in this form. So I didn't just simply rewrite the form. What I did is kind of like above, I said, okay, so I can take the a value and I can multiply it by 1, and that's going to give me that term. I can take b and multiply it by the x, and that's going to give me that term. I can take c and multiply it by that x squared, and that's going to give me that term. So again, this subset S multiplied by any scalar or any set of scalars is going to give me a second degree polynomial or less. It's going to give me something in P2, and in fact, it gives me every possible function in P2. So that would also then be a spanning set of V, or S spans V. All right, so let's go ahead and give a counterexample then. So what does it look like when it doesn't work? So let's go back to the 3 space. And let's define our function, or excuse me, our vector as 1, 3, 1, 0, 1, 2, and 1, 0, negative 5. Okay? So in this case, I'm going to say that this does not span R3, or our vector space V. And the reason for that is because we already know from a previous example that when W was 1, 1, 1, this didn't work, right? 1, 1, 1 is in R3 and cannot be expressed. I'm saying cannot be expressed as a linear combination of vectors in S. Okay, so again, if we go back to example 2, this is this vector space S, right? The subspace. If we go back to example 2, those are back to example 1. Those are the same vectors we used in example 1 and that we used in example 2. In example 2, again, remember we found that when we tried to use those 3 vectors as a linear combination to create 1, 1, 1, we couldn't do it. There was no solution. So that tells me then, it tells us that then S does not span R3, because we find a counterexample, we find a vector that can't be written as a linear combination of the vectors in that subspace. All right. So now let's kind of put this together, and let's actually ask the question then and look at how do we determine this. So does S, and I'm going to change this ever so slightly. I'm going to change my vectors to be 1, 3, 1. 0, 1, 2. So the first 2 are the same, but for the third one, I'm going to make one minor change. Instead of being 1, 0, negative 5, let's make it 2, 0, negative 5. And now ask the question, does this span R3? Okay. So just like before, really what we're asking then is if I multiply each of these vectors by a scalar, add them together, will it give me, as I change those scalars, will it give me every possible vector in R3? Okay, so let's do this. Let's look at those first components. We've got C1, no C2, plus 2c3. And we're just going to set this to some arbitrary value. We'll just call it u1, because in this case, remember, we want this to equal any vector in V. So the second one is going to be 3c1 plus c2. Let's see, no c3 equals u2. And then c1 plus 2c2 minus 5c3 is equal to u3. Write that 5 a little bit more clearly. All right, so again, in this case, it's not really going to help us to create a augmented matrix and try to solve it. But what we can do, and this is going to take us back to something we did back in chapter 3. If we find the determinant of the coefficient matrix, 1, 0, 2, 3, 1, 0, and 1, 2, negative 5. The determinant of that coefficient matrix is 5. And back in chapter 3, we talked about the fact that if the determinant of a coefficient matrix is not equal to 0, then we say that it's non-singular. In other words, because it's non-singular, it has a single solution or a unique solution. Okay. And this is coming from 3.3 if you want to go back and reference. It was one of the last sets of theorems where it talked about equivalency, and it basically said that a non-singular matrix would have a determinant not equal to 0. Okay. So it has a unique solution. So in this case, because that determinant isn't 0, we know that this system would have one singular unique solution no matter what I pick for my scalars and for u. It'll work every single time. Okay. And to be more specific, if I pick values for u1, u2, u3, I will always be able to find a set of scalars c1, c2, c3 that actually makes this system true. If we go back to example 4, if I was to so again, the only difference here is in example 4, I had a 1 here, and now we've got a 2 in example 5. If I change this 2 down in the matrix at the bottom here to a 1, then its determinant is actually equal to 0, which makes it singular, and therefore it does not have a unique solution, which is why in number 4 that subset didn't work. It doesn't span R3. Okay. All right. So last definition before we get into independence and dependence. And this is going to look a lot like what we just talked about, but it's just got a slight little twist on it. It says that if S is a vector space, V1 to Vk, is the set of vectors in a vector space V, so again, a subset of V, then the span of S is the set of all linear combinations of the vectors in S. So basically what this is saying is that the span of S is basically taking every possible combination of vectors and scalars in S. All of those linear combinations create the span of S. Okay, so obviously we can make a scalar 0, which would knock some of those vectors out. We can make them positive. So every combination, right? So these are all linear combinations. That's the span of S. A couple ways to denote it. We've already seen span of S. Or you might just say span of, and then the actual vectors themselves. When the span of S is equal to V, and this kind of ties right back into what we were just talking about, when the span of S is equal to V, in other words, when all of those linear combinations create the entire vector space of V, then we say that V is spanned by those vectors or S, or that S spans V. Okay, so just like up above, we had the same idea, right? S spans V. It's basically just kind of twisting that definition around a little bit so that you can have a span, and the span is just simply all of the linear combinations created by the vectors in S. But when all of those vectors create the entirety of V, then we say that S spans V. It's not just simply a span anymore. It's a very special span because it spans the entirety of V. All right. I'm not going to do anything with that because we basically have kind of talked about that already. It's just, again, another way to think about or talk about some of the terminology. All right, let's go ahead and get into linear independence and dependence then. And so here we now are talking about, again, what makes a vector space independent or dependent. So it says a set of vectors S in a vector space V is linearly independent when the vector equation, you see that there, equals the zero vector. Remember, this isn't zero, it's the zero vector, has only the trivial solution. So in other words, if I take the vectors in S and I look at a linear combination that gives me the zero vector, if the only way to get that zero vector is by making all of the scalars zero, then we say it's linearly independent. If, however, there are non-trivial solutions, in other words, if I can find scalar values that are not zero, that would give me the zero vector, then it's linearly dependent. Okay. So let's go ahead and take a look at some examples here as to what this actually means. So S equals, again, we're going to drop down to the 2 space on this one. Let's use vectors 2, -4 and 3, -6. So again, we're in R2 now. And we're going to say that this is linearly independent. I'm just going to abbreviate that, independent, because I can take 3 times 2 times negative, I'm sorry, misspoke, dependent, linearly dependent, because 3 times 2 times, or 3 times the vector 2, -4 minus 2 times the vector 3, -6 is 0. So in this case, I found I actually found 2 scalars that were not 0 that give me the 0 vector. Okay, that would give me this. So because those scalars are not 0, and yet I got the 0 vector, this is linearly dependent. All right. So let's do another. Let's go, let's determine whether S, which we're going to define as being V1, V2, V3, which specifically has the vectors, let me draw this or write this below so I don't run out of room here. So has the vectors 1, 2, 3, 0, 1, 2, and let's go -2, 0, 1. So the question is this linearly independent or dependent? So we're going to determine whether this vector space S in R3 is linearly independent or dependent. Okay, so again, what we're concerned about here in making this determination is what gives us the 0 vector when we create that linear combination. So if I take C1 times 1, 2, 3, add to that C2 times 0, 1, 2, and add to that C3 times -2, 0, 1, what scalars would give me 0, 0, 0? So again, let's create a system. We've got C1 minus 2C3 equals 0. 2C1 plus C2, no C3, equals 0. And 3C1 plus 2C2, 2C2 plus C3 equals 0. And so again, as always, I'm going to go ahead and create the augmented matrix, 0 or 1, 0, -2, 0, 2, 1, 0, 0, and 3, 2, 1, 0. And applying Gauss-Jordan, that's going to give us 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. So in other words, in this case, again, we're solving for the scalars. So all of the scalars, C1, C2, C3, were all equal to 0. So because of that, and this is obviously a unique situation, so there will not be a case where C1, C2, or C3 is something other than 0, then we can determine that this is linearly independent. Okay? So that's what we're looking for is when you get all zeros in your solution, you get the trivial solution, that's when it's linearly independent. Otherwise, it's dependent. All right. So let's finish up then with just one last idea here. And by the way, there are more examples in the book. So if this isn't enough to really get a sense of this, in the book, I believe it's examples like roughly 9 through 11. They also go through and do the exact same thing, so you can get more idea. And they don't all deal with the three space like this either. So if you want to see some other types of vector spaces and how those are determined, you can go ahead and look at the book at those examples. All right, so let's finish up with this. So basically then we're just kind of turning this into a theorem. It says a set S where you have two or more vectors in the set is linearly dependent if and only if at least one of the vectors v, I can be written as a linear combination of the other vectors in S. Okay, so this is kind of another way to look at this idea. And so this is saying that if I'm going to change this into, we're going to go into the world of matrices here for this one. So I'm going to create three matrices, 2 by 2. Let's go 1, 0, 2, negative 1. Negative 4, 1, and negative 2, 3, and negative 2, 1, and 2, 1. So this is going to be our vector S, and just for clarity while we're talking through this, I'm going to call this V1, V2, V3, and obviously this is now in the world of 2 by 2 matrices. That's our vector space. So again, the idea being that here now it says, so if, again, going back to our theorem, so subspace S where we have at least two vectors is linearly dependent if and only if at least one of the vectors vi can be written as a linear combination of the other vectors in that set. So I'm going to look at S, I'm going to pick one of these matrices and see if I can write that matrix in as a linear combination of the other two matrices in the set. So for example, can I take C1 times V1 plus C2 times V2, and can I make that equal to V3? Linear combination of one vector using the other vectors in the set. All right, so here, and I'm not going to kind of write this out, but so if we look at the first row, first column components, we're basically saying then that C1 times 1 minus 4C2 has to equal negative 2 in V3. If I look at first row, second column, no C1, I'd have a C2 that has to equal 1. And then I've got in the second row, first column, 2C1 minus 2C2 has to equal 2. And then finally, a negative C1 plus 3C2 is equal to 1. Now, in this case, we see already what C2 has to equal. That C2 has to equal 1. So we could just go ahead and plug this in then and notice then, for example, that if C2 is 1, that means that in the first equation, C2 would have to be 2. In the third equation, if C2 is 1, well, now C1 has to be 2. This has to be consistent. And does that work? So if I have 4 minus 2, that works. And if C2 is 1 and C1 is 2, a negative 2 plus 3 is 1. Now, we could obviously show this creating the augmented matrix using Gauss-Jordan. But bottom line is, what we see is that C1 is 2, C2 is 1. So I'm able to write that third matrix as a linear combination of the first two matrices, and therefore S is linearly dependent. So we'll say it's a linearly dependent set. Okay. Obviously, if this didn't work, if we couldn't write one of the matrices as a linear combination of the other two, then it would be linearly independent. The other thing I'll mention is if you go back and look at the equation that we wrote here to get this whole thing started, you might be asking, well, does it matter which matrix you pick or which vector you pick? And the answer is no, because if you notice, I could rewrite this in a lot of different ways. I could move V2 over to the right side, move V3 to the left side. I can move V1 to the right side and solve for V2. So you can basically do this in any order and combination of vectors. It doesn't matter. It'll all work out the same way. Okay. All right, let's finish up with one last example. And let's take S. We're going to go back into the world of polynomials here. Let's take the polynomial 2 plus x plus 3x squared. So that's going to be our first vector. And then our second vector is going to be x plus 2x squared. So again, we'll call this V1, we'll call this V2, and we are now in second degree polynomials. So again, the point of this is the theorem says you have to have at least two vectors in your vector space in order to look at whether or not there's dependence. So in this case, with only two, I'm really just looking at is one vector a scalar of the other vector. In other words, can I multiply one of these two vectors by a scalar to get the other vector in that vector space? And clearly the answer is no. I'm completely missing in V2. I'm completely missing a constant here, and so there's no way I'm going to get a 2 by multiplying V2 by a scalar. The only way, obviously, to lose the 2 in V1 to make a V2 is if I multiply by 0, but then I have the 0 vector, which clearly isn't V2. So in this case, there's no way I can get C1 V1 to equal V2 or vice versa, right? So in this case, then S is a linearly independent set. Is linearly independent sets. Okay? So that's the whole idea behind linear independence and dependence. Some different ways to look at it, think about it, kind of show it. Obviously going back then and tying that into the idea of a spanning set and linear combinations. So that's it for this lesson, and I will see you in the next.